Thank you, dear Uwe, for the nice invitation and introduction. Good evening, ladies and gentlemen. Thanks for listening. I know it's before Christmas, it's evening time, and thanks for your patience with me. And before I start, I'm going to introduce myself a little bit and more or less our institute, because as you see, we have the same abbreviation than you, Uwe. It's ITL in Graz. Yeah. Confusion is perfect. No, we are Institute for Technische Logistik in German, or Logistics Engineering in English. And so I'm showing you a little bit where I'm coming from, what we are doing in Graz, and why I'm standing here. That's the brief history of Graz, where we're a little bit proud of about, because with 200 years, a former archduke, so the brother of the last Austrian emperor, founded this university. And when you come to the university, you see him standing everywhere because he's very present. So all this architecture is from former days, and that's not the only thing here. We made some progress, and as you can see, we grew largely, being now 3,900 staff total at the university, with a federal budget of 209 million. That's, I think, a little bit, or much less than in Dortmund here. But as you see a little bit later, we are technical university, not a full university. So there is three more universities in Graz, two of them much larger than ours. Yeah, because this is split up in Austria. But in Austria, we are only two technical universities, and one of them is Graz. What you can do when you come to studying, it's not so interesting for you. I think you're all beyond this stage. Many different degrees here, but here, this is the structure of the university. We have 7 faculties, and as you see, can see now, architecture is maybe the most non-technical faculty here. The rest is informatics, it's construction engineering, it's machinery, and also some natural sciences. And from this mechanical engineering faculty, where I'm coming from, we have a lot of institutes where here, this ITL, at least not the logo is not the same than yours. We have different color, but the 3 letters. So this is our short history. Our institute, we are total 34 staff, have a typical budget of €500,000, third-party fundings. Let me say, too much lectures because it's a hard work here, and sometimes too much space. As you know, universities, it's always crucial to keep the space because everybody else needed it also. This is what you can do when, in our lectures. Just a brief overview, not to avoid it. Teaching is very essential, and I'm very proud to be honored last week with a colleague of mine did one of the best lectures last year. We got rank number 1 out of 4,000. It's lecturing. From university side, it's maybe not the same than research, but it's essential. We're here for teaching. We're here to motivate and to introduce people into science, and I think this is our DNA. Okay, so that's our institute and our understanding of logistics. As you see, we are in the mechanical engineering faculty. We have a very focused mechanical engineering view on logistics, and beginning on the structural level. And I think instead of the laser pointer here, I'm going to use the laser pointer from the computer. You see here? Yes, yeah. We're starting on the structural level. This is all this network design, logistics and networks. This is why I'm here, probably today, for the rigorosum of Marius Delbrücke, from logistics modeling and material flow calculation. So that's the high-level view of logistics, going down to the system and up to the device level. So we're the engineers that are engineering machinery, building machinery, selling machinery. As Graz, maybe you do not know, is one of the intralogistics hotspots in Europe. We have 2 large producers. I can say their name. It's Knapp and SSI Schäfer. They have together, I think, more than 5,000 employees. only building intralogistics machinery. Yeah. And this is where we are connected on this device level. This is design engineering, modeling, automation, measurement, optimization, and of course, also programming and IT. This is accumulating in 4 research fields. Just a little introduction video running here by side. I'm not going to explain everything in detail, but my focus areas are a little bit more on the higher level. It's intralogistics and logistics technology here. With logistics technology, we have methods for designing and optimizing intralogistics machinery. This is hardly connected to engineering and product development. Taking some synergies from possibly the automotive and the aerospace branch, which is very large also in Graz University of Technology. And this is cumulating and leading into intralogistics, where we are focusing on material flow modeling, testing and simulation, and energy consumption methods, all assigning. What you see in the video, I'm picking out a few examples out of them later, so that we can go into detail a little bit more with this. So, our DNA and what I'm talking about today is in simulation and in the virtual side of the engineering technology. And some abbreviations I'm going to use today, and I'm telling you it will be discrete element method, finite element method, multi-body dynamics, and multi-flexible body dynamics. This is essential to describe the physical side of moving goods. Yeah, means which is the acceleration on the good, which are acting forces, how are goods interacting. We have all these methods necessary to make virtual tests and build up digital twins to optimize the machinery. Okay, back to the title, Beyond Mass, Form and Transit Time. When we look to logistics, transport and more, I think every good lecture presentation should start with some theory. And I found a picture you maybe know, dear Uwe. What is logistics and what makes logistics? And my view on this is, yes, of course, as you wrote it in your book, fulfilling comprehensive goals by managing strategic, tactical, and operational tasks. But how we are managing and dealing with this task is a little bit different. Because where strategic tasks and goals are on the abstract level, it's more a process view on this side. Tactical and operation tasks are dealing with concrete physical objects. Yeah, you see here it's in German, of course, but we have here conveying, we have loading, unloading, we have packaging, we have handling, and so on. We every time have a concrete physical product that we have to touch and to move somewhere, and with these different views, we have on the one side a mechanical view, and I wrote down the number 1687. Any idea where this is coming from? Newton's laws. Yeah, 17th century. And I wrote down logistical view, 1966. This was the founding year of Seoul Society of Logistics Engineers. And this mechanical view and this logistical view on moving goods is a little bit different. So where the mechanical view is physics-based, we are, let me say, we struggle sometimes to exactly describe this physical behavior of the view of the goods, because we have sometimes missing models. I can describe the movement if I let my presenter dropping here, but if I want to describe the impact that will happen when it touches the floor here or the table, maybe there are not enough physical models behind, or they are too extensive, they are too complicated to use them in detail. So we have highly interdisciplinary fields here. We connect mechanics, thermodynamics, electrics, aerodynamics, and so on, because all these physical domains are acting on a moving body. Yeah, and we're talking not more and not less than about the physical moving body. Software here is used since the 1960s. This product name, Adams, that I wrote down here, was developed for, what do you think, 1960? rocket design for the Saturn V rocket. So managing the dynamics of a moving rocket, this was the development stage of this software. On the other side, we have logistical view on moving goods that is mostly fully describable by a question of effort. You can, if you make it event-based, for example, we have maybe fully describable systems up to a very large scale. We have not totally dissimilar submodels. We can describe processes and human behavior on a very abstract view perfectly. It only needs time. Yeah. On the other side, mechanics and thermodynamics and electrics is completely different. Yeah. We have here software since 1982. It was Automot, one of the first discrete element solar. Okay, with these fields, mechanical engineering, mechanical view comes from vehicles, aerospace, is culminating in material handling, in production, and in consumer products. And on the other side, we have fields that are much more broader on the logistical side, customer service. This is out of a logistics engineering handbook, and you're not being ready to fill out everything what is written down here. Just a small view on what is all covered by logistics engineering, logistical engineering here. But we can take another point of view on this topic. Let's see what happens on the negative side. What's the impact if we do not handle mechanics in the right way? We have probably still standing machines because something is broken. We have maybe sometimes serious injury, yeah, because machinery is not working as it should. On the other side, if a process-controlled logistical system is not working, we have probably uneconomic behavior up to systems out of order. Yeah, but we have not this mechanical impact on this side. And I think that's summarizing it a little bit here. On this mechanical side, we describe the nature of the behavior of nature-made systems. So this is all natural science. And we describe here custom man-made science systems because, yeah, it is designed only by our thoughts and not by the laws of physics. Yeah. Diving a little bit deeper into physics and physical modeling would mean to model the interchange and the atomic forces on a molecular level. If you have to describe the movement and the interaction of any physical body with its environment perfectly. Yeah. But we have to cut it somewhere because it's interesting that it is handleable and that you can at least at the end solve everything what you're going to model here. But I hope some pictures will tell more than 1,000 words now. You know the right side. It's a simulation of an intralogistics sortation facility. It's made in plant simulation, event-based, nice simulation. And on the right side, I have some physical simulation examples. What happens if parcels are on a conveyor, or what could happen? So if I only say it's enough to model for this conveyor, it takes 5 seconds from A to B. Maybe something in between can happen. Look at the behavior of this parcel here, the roller transfer. Of course, it's reaching its destination, but it maybe takes some milliseconds longer than estimated because you never modeled this physical behavior before. And yes, we're talking about milliseconds or 0.1 second. But if you enter a transit time or production time here, you enter some digits here and you have to know how accurate your time is if you want to address and if you want to simulate the whole behavior accordingly at the right accuracy. Okay, the same happens on this transfer here. Yeah, it's not a question, does it take longer or not longer? At the end, it's not coming at its end because nobody designed this roller conveyor for packaging and for parcels that look like this. Nobody also designed this conveyor for some small consignments like this. So we have a large shift in parcels and packaging that is on conveying technology and that is handled with conveying technology. And I'm going to show you a little bit more in some more practical examples later. Okay, so summarizing dynamics and the mechanical view of logistics means a local and a global view on the behavior. It means we need dimensions, we need masses, inertias, elasticities, we need the dynamics of the moving goods, and we have the global interaction, we have elasticity and interaction, we have friction and environmental parameters that all influence the behavior of a moving good. It's not interesting if it is a sea container or if it's a small consignment from Courier Express branch. It is probably describable as accurate as necessary, but not fully describable. And we have here on this logistical side, we have an abstract view of a large network that is mainly characterized by arrival times and quantities. Yeah, these are the physical entities you need here. Okay, so far so good. That's the theoretical part. I'm going a little bit more into details and I'm showing you what I dealt with in my last 10 years to make this mechanical side a little bit more solvable. Yes, I took the approach to find the transfer of CAE methods, it's computer-aided engineering methods, from product development to logistics engineering. As you know, your consumer products, your cars, your planes, even our trains are engineered at a much more sophisticated level than our conveyors, than our cranes, and than our material handling equipment. And so I took this approach and showed these branches, what are your methods, what are your software, what is your approach to describe here the behavior, and is it possible to make a transfer? Not to going into detail, it's just some excerpt of my work. And yes, there are some dedicated process chains, for example, to build up digital twins for predictive maintenance that are managing the complex dynamics of goods in product development in operation, and to sharpen these essential parameters that you need when you take a more abstract view and develop some process chains. Not to boring you here with some pictures, just showing here the sources are in the bottom line here if you're interested, how this transfer from, I call them trendsetter branches because in their product development, they're far more advanced than we are in logistics engineering. What does not mean that the one is better and the other thing is weaker, but the effort is completely different. And the engineering department of a large car producer, I think, is much larger than all the intralogistics producers at all. Yeah, so we have a different level of theory and application of modern methods here. Okay, some selected methods. I showed them you a little bit earlier. This was this picture. You probably remember all these abbreviations. But what are we going to do when we use these methods for logistics and for design of conveyors, material handling machinery, and so on? We have some challenges to handle. We have to master non-linear material, and I'm going to show you what non-linear material means. Every consignment, every parcel you order is highly non-linear. The carton crashes, it changes its shape when you touch them. This is really hard to describe. Yeah, but it's essential. As you see, remember the jumping parcel on the conveyor. If I cannot describe the interaction, I cannot understand its behavior. And yes, we can answer this, and this is also out of my research, not to detail it here, because I want to show you some examples. My first example is from automated logwood handling. Austria is a country full of trees. Germany also has a lot of forests and trees, but we have a really big wood industry in Austria. What this has to do with logistics is, yeah, you have to bring out the trees out of the forests to the sawmills or to the producers. And there comes the topology in Austria. It's mountains, it's winter. It's hard to harvest them. It's hard to transport them. You have to load them. You have to unload them. And there is much potential for automation because we have a task that is highly risky and very dangerous. And I'm showing where we can do something with automation. I asked ChatGPT, make me a picture of logwood handling, and this came out. And yeah, you know, it's you take a much more detailed view, and you find hundreds of errors. And I do not know why the logs are jumping back again. But yeah, this is AI graphics, maybe to bring a little bit of a smile inside here. But this logwood handling is a highly risky, physically demanding work, and we have a shortage of workers. We have this very dangerous work, yeah, and we have therefore high potential for automation, not only for the handling, but also for the self-driving truck into the forest. When there are some ongoing research projects at the institute, and just we run last half year a large, it's called COMET project. It's one of the largest Austrian research project Modi, where we're dealing with the complete truck, how you can handle these logwoods automatically. But why is the knowledge of physics here interesting? Okay, we do some image recognition. You must detect the logs, but detecting them is not okay. You can make a picture, and if you train some neural networks, they say, okay, that's logwoods. But what is interesting is where is the center of gravity? Because I have to pick up the log into the center of gravity. Otherwise, it would happen this. Yeah. We need automation of safety critical and labor intensive processes in forests, and we do autonomous forest logistics if we can describe all this physics. And this is what I'm showing you now. This is a typical loading process. And now, question for the auditorium, where is the difference? The most essential difference, of course, this one is a picture. Here is a simulation screenshot, but something is missing at the right side. Yes. Thank you. Yeah, of course. The operator here is missing. Yeah, and the cabin is missing because the crane is doing this work automatically. Not to promise too much, we can do it for now. We are not as fast as the good operator, but we can do it. And at this time, when we are doing it, the operator can do something else. Yeah, having lunch or going to the tree, cutting the next tree, to the forest, cutting the next tree. And there is where this great automation potential here is settled. But why is the physics so important here? You see this crane, it's one of the biggest producers of logwood cranes. It's called Palfinger. Maybe you heard of them. It's an Austrian company. They're producing for the whole world, and the market is really international. Yeah, modeling this crane is not as easy as it looks like. Yeah, you can build a model, but then some question arise. What is about this hydraulic cylinder here? How is its behavior? For example, when the oil is cold, when the oil is warm, when the oil is fresh, when the oil is not fresh. How is this behavior of this beam here? Is it rigid or is it elastic? Yeah, and all has to be considered in such a model. And just some insights here on a very high level view. You see here all moving parts in this model. You see the connection to the hydraulic simulation model. We have a key technology here that means functional mock-up interface that connects different simulation domains. Remember, we talked about physics, we talked about mechanics, aerodynamics, thermodynamics, and so on. We have to connect them all. This is by functional mock-up interface is very good possible here. And we're going much more into detail. We are introducing here non-rigid bodies because this beam, one of these logs has 400 kilograms. The crane picks up 2 or 3 of them, is elastic, and it deforms here elastically. And we have to consider it, but because if it's bending, and I do not know how much it's bending, I never hit the target. Yeah, so I have to describe this, but this is possible in modern engineering methods, but it's a question of effort, and it's very time consuming and calculation intensive here to make these simulations here. Okay, some software products just mentioned here. MSc Mark comes from nonlinear material simulation, and this is very much appropriate here to model, for example, the behavior of this crane. But the key is in reducing these models. As I addressed in the beginning, it's not possible to model it completely or exactly. So we have to cut a certain layer and say how much of this behavior of this very complex structure is interesting for me, and how much do I have to consider to model enough that the whole automation process is running. Okay, here are some insights in what we built in the control algorithms, and here is some insights. It's not that sophisticated than what it is behind. This is this whole combination of different simulation domains, where this gripper here does its first movement on the screen. Yeah, to transfer it to the real operating crane is the other challenge. But this is here one of the main advantages of virtual engineering. We can test much of our equipment, of our processes, and of our behavior on the screen. And it's not only faster, and it's not only more performative, it's at the end more safe. Yeah, because when we turned on the automation the first time on the crane, it made like this. Yeah, and the exit button did not work. So yeah, we disconnected some of the computer cables so that it stopped again, because all this testing should happen on the virtual side. Yeah, you see the loading process here. Yeah, you can tell me, okay, my computer animation also does this. Yeah, and I have a computer game that looks like this, and it's the same. Yeah, we are not talking about visualization. We are talking about simulation, and for me, it's important how large is the force here and how large is the acceleration here. And it has not only to look good, but it's the difference to some computer games where you see all these moving parts. Also, very performative running, for example, on your smartphone. Yeah, this needs high performance computers, and I think this simulation model runs for 30 hours and more only to make one turn of this crane here. Okay, long story short, here's the first prototype of the automatic. You see, we have the cabin here, but we have no operator. And yes, we do not have a remote control somewhere in the backyard. We have a complete automated loading of one, we call it Polter. I have no idea what this is in English. This is this collection of locks here, where it is loaded completely automatically on the truck. And yes, every good operator would do this movement much better, you know, but the first step, and we do not need the operator. So we have one person, a qualified person. They're all highly skilled workers that has not to do this simple crane movement. He can do the work in the forest. He can do other work. What is his intention and what he is usually used for. Okay. At the we have it here at this left bottom side here. You see the image recognition. It's turning from the camera view to this recognition view. And yes, we have to pick them in the center of gravity. And these are very homogeneous locks, but we have not every time homogeneous locks. Yeah. So the algorithm not only makes the photo, not only identifies the lock, it calculates the center of gravity. So I have to pick it exactly there. Okay, it's really new video. It was shot last week. Okay, so we developed in a structural process, a digital twin, not only for the engineering process and the development process, but also for the automation process and the software control at the end, and can make this process here much more performative, avoiding dangerous operations and using skilled workers for the skills that they are usually employed at the producer. Yeah, the digital twin here is the powerful development tool with the reduction of development time and costs, early identification and correction of errors. I spoke about this turning crane. We did not find every error in advance, but we found many of them when we tested the automation. And we can, of course, simulate much more scenarios on the virtual side than in the forest because we have more time, can use more computers in parallel, and we have more abilities because not everything, this test stand is very expensive. We have to run the truck the whole time. The truck cannot work in the forest at the same time. So once the model is ready, we have here a big advantage. What's the overall advantage of a digital twin? Okay, my second example is about automated biomass handling, and we're staying in the area of cranes, but leaving the logwoods up to wood chips now. I'm showing you out of it. It's a Horizon project we have at the Institute. Yeah, I'm not talking about all this. It's thermodynamics that is burning wood chips, and it's a very innovative process with a novel updraft gasifier connected to a heat pump, connected to gas reformation, using the ash as fertilizer, and so on. This okay, shoot me that. That's not my my domain. But my domain is we have to provide this gasifier with fuel, yeah, and we have to grip the wood chips and bring it to the burner. And conventional conveyors, they take what they get because you have the storage bunker filled with wood chips, and at the bottom you're pulling out what's lying there because you cannot choose. Yeah, it's the conventional technology. And we found another approach I show you with a gripper, but we must know also some physics of our goods. We must know the mass, we must know the humidity, and we must know the ash content to provide the right quality at the right time with the right product. I do not have to speak about the 7 hours in Dortmund, or no, everybody knows. Yes, of course. That's a classic example. Instead of pulling out at the bottom the wood chips, we pick at the top, but we choose what we're picking because we can measure. Here is the good material, here's the wet material, here's the less good material. And they're showing you how we're doing this. Okay. This here is the automated gripper. It has a camera and a humidity detection system. Yeah. And we have different storage bunkers. We grip from the top, we measure, and we're sorting. When the burner is not working at full operational load, we can use the gripper for sorting the material. You never get homogeneous wood chips. You have from one forest, you have from another forest, you have from one supplier, from another supplier. They're all different quality. But if you provide the burner with the right quality, you can improve the overall efficiency. You can improve the ash content. You can improve all the emissions because you can bring the right material for the right operational stage. Yeah. For example, in full load, you can burn everything, but in partial load, you need the good material and you have to choose. And this is what we're doing here with this automated gripper. By the knowledge of physics, which are here a little bit different. The physics here are humidity and ash content. Maybe it's more chemistry than physics, but measuring this is the key of this automation concept. At the end, we developed this automation of the crane and the algorithm, how it mixes together to provide the right quality here, this burner at the different stages of combustion. Okay, my last example, I think I'm a little, time, comes from Curie Express branch, and is describing the dynamics of consignments, shippings, goods, parcels. Call them how you want. If you take a look to literature, you find many different words which all are describing the same. It's for us, it's a parcel, or it's you are shipping, or it's what you ordered yesterday. And why this is so important, I can show you in the next few slides, hopefully. With all this e-commerce boom, we have a constantly increasing volumes in e-commerce, and the consignments change so rapidly that we cannot even describe them with words, not with physics. Nobody knows how to name this parcel here, the green one. Some say polybag, some say flat, some say Tüte, some say Plastiksackerl in Österreich. Ne? Some years ago, a parcel was a parcel. It was a six-sided carton. Yeah. And we have now dramatic change, nearly in a half a year cycle, from one consignment type to the other. I asked ChatGPT again, draw me a picture of loading and unloading parcels and sorting them. A little bit more interesting because they're dropping down from somewhere and here out of the truck, but he used different parcel types. This is why I used it here for my presentation. But why is the knowledge of physics here so important? And which physical parameters do we have to know? It's for the first, like everybody would have assumed, mass. Mass of the consignment is what you're paying for. If you go to the postal office with your shipment, they are laying them on a way, yeah, and say, okay, X kilogram makes so much euros. But there is something more. For example, J is the moment of inertia, how it's resistance to movement. Yeah, it's something more. It's what about the flexibility of the parcel? Yeah. Some years ago, parcels, I told you, were cartons, and cartons were dealt as perfectly stable, yeah, or elastic. But these consignments are not elastic. Once you touch them, they lose their shape and they never return in the same shape. This is non-linearity. And so if we here provide all the processes with image recognition for detection and classification, if we are wanting to build new machinery, optimized machinery that has never been developed for handling consignments like this, because they were all developed for six-sided carton puzzles, we need to describe the physics. And we have now the third research project in Graz with describing the physics of moving goods. And I hope my next pictures will show you what I'm speaking about. Yeah, that's what Courier Express companies have to deal with. Yeah, that's polybags. We call them, and we defined it in a research article, what a polybag is. They coming as bulk material. You have a container full with bulky polybags. Yeah, you load them out on a conveyor, and what's the behavior of this bulk of parcels? Yeah, nobody can describe so far. But when you want to design it, you have to classify them before, because not every of this polybag is non-linear in the same dimension. Yeah, one is more rigid, one is more stiff, one is perfectly linear, one is non-linear. And this is our first approach here. We developed an algorithm to classify shipments. Yeah. This is what came out. We classify them by shape, by dimensions, by another shape parameter, and so on. It's just one side, but you see here the different examples of shape only if you have to classify them. And we do it by image recognition. We trained an algorithm to divide between carton and polybag and flat and round and so on, so that we can say, okay, in this bulk, I have X polybags of polyurethane, for example, and I have Y polybags of flat carton. And this classification comes before optimization, because the physical behavior of these classes is highly different. Yeah. Okay, this is one picture of the ongoing PhD. One of my candidates is going to finish next week. Okay, so that's the real world. You all know that's a sortation center, cross-belt sorter here and some chutes here at the end. We built a test stand to model the physical behavior. It's a very simple test stand, only testing the friction and to analyze this impact if it touches another conveyor. And then here is the real big virtual world. What do we have to model and how good can we do it? And I'm not showing you the details now because this is much too complex and I'm not into the details. These are my PhD candidates. They're really good in this. But I'm showing you the impact of this modeling. Remember these jumping parcels on this roller conveyor, the red one from the beginning? We can now in simulation and in the test stand really exactly describe the physical behavior. And yes, every second counts, and it's not the same if it needs 1 second or it's 1.1 second, because there is a difference. And if you do not model it in this logistical domain with the physical knowledge, you cannot describe it as exact as it's necessary. We can describe the behavior of these flexible bodies. See here, okay, this should start here with one moving parcel. We have now 4 moving parcels here. All this is really, really time consuming. This simulation runs for, I think, 70 hours or longer, and it's only 4 parcels. Remember these chutes full of polybags, hundreds of them. To simulate them, we are using some reduced approaches. As I mentioned in the beginning, not to model it in the last detail, but to model it accurately for the interesting purpose and for the modeling purpose. Okay, here in RBG colors shows the flexibility and the resulting stress on the parcel here. Yeah, it describes the behavior. The last simulation, and the colleagues came back from a test run in Nuremberg. We're working together with Körber Industries and the Austrian Post here on this project. They did it with 10 parcels now, modifying, simulating, and analyzing the differences between experiment in the field on the test stand and simulation at the other side. And there are real good approaches here to model this complex behavior. But where does this result at the end? One interesting side aspect of all this modeling was, we do not only have to handle on conveyors the parcel, we also have to load and unload trucks. And one very good example, you see a little spoiler here in the last time, what I'm going to show you in my last minutes here is, yes, we developed an unloading device for parcel trucks. All your Christmas presents in parcels from e-commerce are loaded and unloaded manually into a truck and out of the truck. And I did it for a few hours in a sortation center, and I can tell you this is real hard work. To unload a complete truck in 1 hour, it's around 30 tons of parcel you have to pick and place on the conveyor. It's real physically hard work. We did not solve the loading problem so far, but we solved the unloading problem, and I think this video shows more than my words. We developed a new swap body, and this swap body contains a moving floor that is pulled out and directly connected on the conveyor technology of the sortation center. There's a video that 6 of these installations are running at Austrian postal hubs. It was a former startup. It's PHS. It's not in operation anymore. These were my 2 doctorate candidates 10 years ago. Together with Austrian Post, they founded this startup. They got sold to Kalyan. Maybe you know them. It's a big producer of conveyor technology. And yes, this product is on the market. It's now called Auto Unloader. You can buy it if you want, and you have a sortation center at home or have to unload a truck every day. What's a great advantage? You can see here in this video here, this blue device connects automatically to the truck. It recognizes the truck, it knows where the truck stands, and it pulls out this moving floor. And one of these blue devices can operate many doors at the same time, because the unloading process got about 3 to 4 times faster than the manual process. Yeah. And at the end, you do not only have this advantage in time, but you have also the advantage that you know which parcels are coming, because it's fully camera observed, and you know which types of parcel. Remember this classification scheme can say, okay, I have X polybags, I have X cartons. You can bring this into the control, into the system of the whole operation of the sortation center. And it's a real nice product. We are very proud of. Yeah, it started with some simulation. And honestly, this video, what I'm showing you here, it's not simulation, it's visualization. It's from Cinema 4D. It's a complete visualization software. But of course, we started then after this promotion video with this physical behavior, describing it, because it's important to know this physical behavior. The parcel should not drop too much. You must calculate how much parcels you can unload in the right time. I think this is one of my last slides. Just answering hopefully some questions. Why physics details matter in logistics? Yeah, because movement of goods is complex. Yeah, every second counts, or every millisecond counts if you have to describe them exactly. And this is the transfer potential from the mechanical side to the logistical side, to know these milliseconds better, or to know the deviations better, or to know the scenarios better. And yes, interaction occurs. All this bulk handling of goods shows that not only one good is to describe, and that interaction occurs. Yeah, durability and wear is essential. We need safe and safe operation that is required, and we have to describe all our mechanisms here. And yes, with all this virtual side, we can support complex approaches like the image recognition process. It needs to know where the center of gravity is. We have to provide the automation with all these physical details. Remember, the ash gripper has to know how humid and what is the ash content of the biochips, not the ash. And we use all this, like where these tools are coming from, with optimizing and developing new machinery and processes like these unloading devices. And yes, and why engineers are still necessary in this AI age. If you take the closer view to some ChatGPT pictures, told him, okay, here is my presentation, make an overall picture. Oh, here is physics in material handling. And yes, of course, it looks nice, but it's completely rubbish. Yeah, because none of the acting forces here is right. Friction force, FR, never acts in a vertical dimension. These angles here, it's nonsense somewhere. Not saying that in a few years it would not be appropriate to build some physical models, but for now it's not enough. And my personal takeaways for you, these are on a completely different side, but addressing something what I learned in I've now 25 years in Graz dealing with this kind of research. Yes, do the right things, and not everything feasible makes sense. Yeah, there's a nice painting. It's called the Turmbau zu Babel. Yeah, you know how the end of the Turmbau zu Babel is? Babylonian speech confusion. Yeah, we do not need this in logistics. We have to talk the same language. Yeah, no speech confusion. So if you do not do the right things, maybe that's the address to us as researchers. We're good in doing things right, but what are the right things? What is important for the future? We have to talk with other people. Yeah. Next thing, as I'm coming from Austria, I'm not sure if anybody remembers this. Genesis is Skynet. It's from Terminator, when the machines take over the control. Do not feed the AI with everything. We're producing data, we are producing insights, we are producing knowledge. Do we have to feed the machine with everything? Yeah. In my second passion at the Graz University, I'm in the ethics commission. We're discussing hardly what it's not. We're not talking about data protection. We're talking about knowledge protection. What can we feed the machine? Which machine can we feed with which data? Because the end, you should take a look to Terminator. Why I'm telling you, of course, Arnold Schwarzenegger is Austrian. Yeah, he's the Terminator. And remember, Genesis is Skynet when the machines take over control. Michael den Hoppel made a presentation 2 weeks ago in Graz at the conference of mine. It's at 27. It's the single point of no return. Yeah, so remember. Yes, and of course, stay interested and connected. Just a small advertising, our VNL network, where I'm also making some work here. It's Verein Netzwerk Logistik. It's like the German BVL, but in Austria, it's a little bit different. Yeah, last advertising, yeah, physics matters, and you can find it here. It's new Handbuch Logistik, where I made a chapter of sortation systems, and we finally have the new edition of sorting and conveying systems next year ready. So it's camera ready now, together with Michael den Hompel and Alice Kirchheim. We integrated all the new technology, also the physics and the simulation side. Okay, I think this was 5 minutes too long. Sorry for this. Thanks for your understanding and listening. Thank you.